This is video 6 in our series, Analytical Mechanics. A reminder that the playlist for all the videos is found at the website digital-university.org. In this video, we want to spend some time and just look at a very simple harmonic system. We'll apply this to elementary calculus, but I think you'll see that even with this not just a simple system, but probably the simplest of harmonic systems, there really is a lot to think about. So we thought we'd just sort of go through it step by step and try and discuss some of the more important features of it. So here we have a spring, and there's a small mass attached to it. And we imagine that we pull the spring out at some distance. We'll call that A. Let's notify it like this, at a distance A, and then we release it. Of course, what's going to happen is, imagine this is just a frictionless plane, so that now the mass is just going to move back and forth like this between minus A and plus A. And this is an x-axis, and we'll say that positive x is to the right. And A now, or A, let's just have it like this. This is the displacement is x. In other words, here it is sitting right here at equilibrium where the spring is not stretched, and then any stretching of it is in the x direction. So when we say x, we mean the distance from equilibrium, and then the maximum that x can have will be A. That's the amplitude. And we know that when we pull the spring out, there's a restoring force that pulls it back. And if we don't go beyond the elastic limits of the spring, that the elastic force is proportional to that distance. And in fact, there's a spring constant here, and it's a minus sign because we're pulling it in this direction, but the force is pulling in the opposite direction. Here we also know that for this type of system, that the kinetic energy, and in this video we'll have U to designate the potential energy, when you add them together, that gives us the total energy of the system, and that is a constant. And since this is a conservative system, then that means that this force, F, that is equal then to the negative derivative of the potential. And we're not showing this as a partial potential because we're only working in one dimension, x. So from this, we would have then that minus kx, that's what F is, minus kx equals this. We can forget about the minus signs then, and we would have that du equals kx dx. So if we integrate this, and u, remember, is the potential energy, k is a constant, so that will come to the outside of our integral, and we are measuring this now x. So x then starts here at the equilibrium point, goes from 0 to whatever point here of displacement we are at. So it just goes from 0 to x, and then now 0 means right here at the equilibrium point the string has not been stretched or compressed, and here we would say a potential energy U of 0, and here U of x. So this is pretty simple. We have that U of x minus U of 0. This is just going to be 1/2 x squared. So you have k times 1/2 x squared. And x is going from u to x, which is going to be this, and we can say, well, when we're right here at u of 0, we can just call that the zero potential energy if we want to, because we're always, in a problem, we're always interested in what is the difference of the potential energy. So we can call that 0. That can be our 0 point, our 0 reference point for the potential energy. And we have then that the potential energy of the system equals 1/2 k x squared. So that was pretty easy to derive. Now, what would be the maximum potential energy? Well, obviously then when x is at its maximum value, A. So we have U maximum will equal 1/2 k times A squared. Now let's remember this, and we'll rewrite this. So what we want to do is, this is obviously the equation of a parabola, so we want to kind of make a rough graph of that. So we're going to erase all this and make some room and do that. So we have t plus u equals E, which is a constant, and we also have that U, the potential energy, equals 1/2 k x squared. So let's just draw a crude graph here. This is x, this is energy. So the plot of the potential energy is going to be some sort of parabola like this, where this is A, the maximum amplitude, and over here this would be minus A. And let's consider this for a moment, where we have t plus u equals E. Now, obviously, as we pull the spring out further and further, or compress it more and more, the potential energy is going to keep increasing then because of this x term. Well, if this increases, then, and if this is constant, which it is, then obviously the kinetic energy has to decrease. Well, when this is at its maximum value, when we have the maximum displacement then, when x is equal to the amplitude A, at that point the kinetic energy is 0. So we have that U maximum equals E. And likewise, we'll find out in just a few moments that the maximum potential energy, then that's going to be 0, and that equals E. So we have that the maximum potential energy is going to be equal to the maximum kinetic energy. But right here then, this is the energy axis, and right here, this is the total energy of the system, that horizontal line. So at this point, that distance right there is 1/2 x squared. And we don't need this any longer. Now, at this point, when x equals A, then obviously that point is 1/2, this is 1/2 kx squared. This is 1/2 k times A squared. So this horizontal line here would have that value 1/2 Ka squared. Now this in between, this is the potential energy, this is the total energy. It can be equal to the maximum potential energy. So this right in here is the kinetic energy. So we have then that the kinetic energy is equal to this 1/2 Ka squared minus this 1/2 Kx squared. So we have T equals 1/2 K times A squared minus X squared. And we say the potential energy, or the kinetic energy, obviously referring to the kinetic energy of the block. So we have then that, and the kinetic energy of the block, that's 1/2 mv squared. So these will cross out, and we get that the velocity of the block, that will equal plus or minus the square root of K over m times the square root of A squared minus X squared. And again, we're showing that when X equals A, when we're at the maximum displacement, the velocity is 0, the kinetic energy is 0, and it's entirely consists, the energy at that point when X equals A consists entirely of the potential energy. Now, what happens right here? X is 0, and the potential energy is 1/2 Kx squared, so that should be 0, so there should be maximum kinetic energy then. Well, let's see. Let's take the derivative of v with respect to x, and we're going to consider we'll work only with the positive value. So we'll have dv dx will equal the derivative of this with respect to x. So let's consider this not as a square root, but raised to the power 1/2. So that will be 1/2 times the square root of K over m times A squared minus X squared to the minus 1/2 times the derivative of what's inside, and that's going to be minus 2x. So the 1/2 and the 2 will cancel, and we have that dv dx will equal the square root of K over m divided by, that's a minus sign, so this will be in the denominator, square root of A squared minus X squared has a minus sign, times x. And that is dv dx. And of course that will have a maximum or a minimum point when it equals 0. And dv dx will equal 0 when x equals 0. So dv dx equals 0 when x equals 0. Now the question is, okay, but is that a maximum or a minimum value for dv dx? So to know that, we'll have to take the second derivative and see if the second derivative comes out positive or negative. So we'll have d squared v dx squared, and that will equal, now remember, let's put this, in fact, let's just work it with this form right here, it's easier. Here we're going to bring this down, and we have this minus sign, so we have this will come down to here, and we have that minus sign there, so they'll cancel out, so we'll have 1/2 the square root of k over m times this, a squared minus x squared, negative 1/2 minus 1 is negative 3/2. Then what's inside will be minus 2x. So notice this is positive when x is positive. That means then that this will be a maximum value. Now, if we had worked with the negative part here, then when we take our second derivative and x is negative, then that still comes out to be a negative number. So what that means is that this velocity is at a maximum whether we're going like this or going like this. So what that means is that, going back to our diagram, that the velocity is a maximum when this is right here at its equilibrium point, at the place where the string or the spring was not stretched. Then it goes over to here, and now it's going back to that equilibrium point from the opposite direction. Therefore, the velocity will have an opposite sign. But again, it will have its maximum value right at that point. So we just went through this and took that second derivative to assure ourselves that indeed when this equals 0, that is a maximum velocity. So we can erase this. Don't need this any longer. But what we have then is that the maximum velocity at the block is right here, or that'd be right here, and since that's the maximum energy for the block, and since the mass of the block is constant, then that is where the kinetic energy has its maximum value. So the kinetic energy has its maximum value here. The potential energy has maximum value at the maximum points of displacement. Let's see, is there anything else that we can derive from these equations? We have now from here that the maximum potential, or the maximum kinetic energy, equals the maximum potential energy, which equals the total energy of the system. Now, and why is that true? Because here, when we have our maximum value for the potential energy, that's 0. When we have our maximum value for the kinetic energy at this point, then U is 0. So the maximum potential energy, that's the total, that is equal to the total energy. Likewise, the maximum potential energy is equal to the total energy. So we have here then, and what is this? Well, this is 1/2 mv maximum squared. And what is this? Well, that's 1/2 k times a squared. So from this, we'd get that the maximum velocity of the block equals plus or minus the square root of k over m times a. And again, the plus or the minus means whether we're going in this direction or whether it's moving in that direction. But that's one way of expressing the maximum velocity for the block. We also have the maximum kinetic energy equals the total energy. So we have 1/2 mv squared maximum equals the total energy. So from this then we would have that V maximum equals the square root of 2 times E over m. This is m over 2, 2 over m, take the square root, and it'll be plus or minus, depending upon which direction we're going. But anyway, here are then two expressions for the maximum velocity for the block. But let's go to here to this expression. We had derived that V equals plus or minus the square root of K over M times the square root of A squared minus X squared. And what we're going to do is work with this equation so we can get more information about the system. But we've been going on for a long time in this segment. Let's stop the video at this point, and when we come back to the second half of the video, we're going to be considering, obviously, the same system, but where we're going to pick up from is we'll start working with this equation and see what new information we can obtain about the system. So come back and join us for the second half of the video, and we'll continue along here with our discussion.